apparently, you guys are shifted ahead of time a little bit from the schedule. It's a good thing I tuned in.
Yes.
Sure, I'll start now.
Okay. Wow.
Let's get that share screen going. Adjust something. Get this back to the beginning. All right, so this talk is about knots and knotted vortices. And I'm going to begin by talking for a little while just about topology and knot theory. And then I will talk about some phenomenology about vortices in fluids. And then we'll look at some topological problems about vortices. This Escher drawing is worth thinking about if you're a topologist. It embodies some nice features about Mobius strips and knots, so I thought I would mention it. You've probably seen this Escher drawing before, and there are some features that are purely artistic. He's drawn it as little planaria that meet head to tail and form well, they form a Mobius strip if you were to fill in this intermediate part here. But it's a 3/2 twisted Mobius strip. And as you see, this is the result of cutting the 3/2 twisted Mobius strip right down the middle, never mind the eyes of the planaria. And you see a trefoil knot. And this is a very nice experiment. You should perform it. Take a strip of paper, form a 3/2 twisted Mobius, and then cut it down the middle, and lo and behold, a knot appears. And Escher obviously was fascinated by this phenomenon and made this famous woodcut. Now, the problem in topology is telling whether something is knotted or not. As I said, I just want to chat about topology a little bit. So here is a tube, and we're thinking of it as a flexible tube in three-dimensional space, but it's rather woven. And you might think, well, maybe it's knotted in the sense that you can't undo it if you're allowed to move it flexibly. But you'd be wrong. It's actually unknotted. And if we had some time, I would show you a film of it being unknotted. But if you want, you could try to visualize the unknotting of this. It's hard. It's hard to see whether something is knotted or unknotted, and that leads to the mathematical problem, of course. So what one is looking for is some property of the space, of the topological entity, that doesn't change when it's being deformed. And one way to do this is to go to geometry. Here's a trefoil knot, but it's made as straight lines in a rectangular lattice, and then it has a very specific kind of geometric form, and this geometry is inherent inside the topology and is one way to look for what goes on. So there's always this interplay between geometry and topology in realized objects. Now, on the other hand, you can see some aspects of things that are certainly going to be properties of a system like this. Here's a link, a simple link. There are going to be properties of a system like this that are independent of deforming it. These two rings are linked around one another, and if I were to take this golden ring and start pulling them on it without tearing it, of course, they would remain linked with one another. And in fact, there's something you can count. You can count how many times the golden ring goes around the blue ring, and as you see, it's once. And if you count in the correct way mathematically, it will always come out once, even if you add a more complex, deformed version of it. So there is a notion of linking number. And linking number, in fact, was studied by Gauss and Maxwell and people like that in the 19th century, and for good reason, because one had the beginnings of the electromagnetic field, and one needed to count how many times how an electromagnetic field would flux through a given surface, and so linking number was studied for those reasons. On the other hand, and let me see, yes, I have a picture here. On the other hand, there are configurations like this one where there are no linking numbers. If you look at these Borromean rings, and you were to, in your mind, let's say, remove the red ring, then the other two are unlinked from one another. And any two of them are unlinked, but all three of them are linked. And so this requires some subtler kind of mathematics in order to articulate a property of them that doesn't vary under deformation. So I'm now going to talk about a couple of different ways of measuring things topologically. And here I can trace an idea back to a non-topological source, but it isn't where the idea came from for me or for us, the non-theorists, but it's a well-known idea. If you look at this book by Romilly Allen about Celtic weave, then you see that he systematizes how to think about Celtic weave by suggesting that you as a designer could start with a rectangular alternating lattice weave like this, and then you could take some of these crossings and you could replace them. You could cut them out and then reconnect them like this or like that. And this reconnection theme is the theme of my entire talk, actually. And if you do this and take a look at the weaves that people produce, maybe I'll magnify this if I can. No, I can't. But if you look at this Celtic weave over here, you see that it is in fact made from a rectangular lattice weave by re-smoothing some of the crossings, and depending on what choices you make, you get different patterns. So this is a good way to systematize at the base how Celtic weaves are made. What would this have to do with topological properties? Well, 83 years later from Mr. Allen, your lecturer wrote down this equation. Of course, Romilly Allen was not making equations and he wasn't looking for topological properties. But the idea here is that you would have some kind of number or polynomial, some mathematical expression that you would associate with the knot, and that this mathematical expression would obey a recursion relation like this, that you could make a different weave by reconnecting it this way or reconnecting it this way, and that the evaluation of this would be equal to a sum of coefficients times the evaluations of these related and simpler weaves, and then recursively you could calculate this, and then you could try to adjust the coefficients so that it was topologically invariant, that it didn't give you any different result if you deformed the knot or the link. And this in fact does work, and calculations look like this, you see, that you would start with a knot and you would look at the two different ways of reconnecting it. And it doesn't matter here about orientation until later, so you just look at the two ways of reconnecting that, and then look at the different ways of reconnecting those. And when they turn out to be just little curly forms, there's a way of evaluating them. So in this case, you end up at these three basic entities that can be calculated, and you add them up appropriately, and you end up with a polynomial which doesn't change when you move the knot around. That's not obvious, and I won't go into the details of how it works. It's not complicated, but it's subtle, and it lets you prove difficult things about the knot, like the fact that the knot and its mirror image, see this knot and mirror image, I switched all the crossings, or you can think of this as the image in the mirror. So there's a left-handed trefoil and there's a right-handed trefoil, and they are not deformable into one another, and measuring in this way can prove that. So these measurements that we make by calculating on a given diagram of the knot, they capture properties of the entire infinite collection of configurations of the knot, because if you move in that collection of configurations obtained by deforming it slightly, you can get very complicated things. They all will give you the same resultant polynomial, because the polynomial is invariant. These polynomials are analogous to statistical mechanics functions. You see, you've made at every choice in the knot a choice, a binary choice, smoothing it one way or re-smoothing it the other way. And so there is a power of 2 number of configurations, and one is summing over the contributions of all these configurations. Exactly analogous to forming a partition function in statistical mechanics. And these partition functions are topological, and they are adjusted so that it doesn't matter what happens when you deform the knot. So that's an idea that began in the 1980s and turns out to be very fruitful for understanding how to get at topological properties of knots and links. This function of states that I'm saying looks like a statistical mechanics function was reconfigured by Mikhail Kovanov back in 1998 by thinking in the following way, that you have a special way of designating the smoothing, and then you can re-smooth it. And when you re-smooth it, you think of an arrow which goes from one of these states to another. So in this case, this state got re-smoothed into that one, reconnected from here to here. And then another reconnection took you here, and eventually you went into the entirely B state of reconnection from the A state of reconnection. And you can choose A versus B by using the knot diagram itself, by using the kind of crossing you're looking at. You see, the A types are when you smooth the crossing this way, and the B types are when you smooth it the other way. And I won't bother you with the convention, but there is a definite distinction between this way and that way, coming from the fact that you can rotate the overcrossing line counterclockwise and it sweeps out the A regions. So Kovanov said, oh, arrows between them, arrows to show you the ordering from one to the other, and then it forms a category. The category is simply a structure with objects, and these are the objects, these states, and arrows that go from one object to another. They aren't functions, they're just relationships. And so there's a category here, and he asked, how can we obtain topological information from this category beyond the kind of polynomial calculation I'm telling you about? And he succeeded in doing that by a method which I'll explain a little more about later, because it comes into our study of the vortices. So that's one example of getting invariance of knots and links. Now I want to show you another one which is very elementary, just so if you wanted to think about topology of knots, you could go off and fool with this yourself and see what you can do with it. I'm going to look at a knot as a diagram, as a projected diagram, and then it consists of some arcs, you see. The green arc here is this one here that I've labeled A, and the red arc here is essentially, oops, I think they were imaged or something. Anyway, these are not perfect images of one another. The one is rotated. It doesn't matter. There are 3 arcs. And over here in this picture, one is green, one is blue, and one is red. Over in this picture, one is B, one is C, and one is A. One is brick-hatched, one is cross-hatched, and one is solid. And I'm thinking of 3 colors on the diagram in this way. So now I give you a rule. I'm going to play a game on this little game board of the diagram. The coloring game is that you either see three colors that are crossing, like here, green, red, and blue, or you see one color. And in this case, there isn't any example of one color, but we'll have one in a moment. So this is a coloring, a three coloring of the knot. And now we're going to play the following game. Let's move the knot around, deform it, and watch what happens to the coloring. And we'll see that we can preserve the coloring when we move the knot. So here's the knot, three colored, and I want to push this arc underneath like that. Well, so I push it underneath and I leave all the coloring the same as it was before, but you see that now this color meets a different color and gets the third color, and that's consistent over here, so that this deformed diagram is still three colored according to my rules. And then I pushed it up under there and it still worked. And then I pushed it up under there and it still worked. And there we are. And now I'm pushing brick hatched against brick hatched, and so it stays brick hatched. At this point, I use the other side of my rule, 1 or 3, remember? Every one of these crossings has 3, but this is 1. And that's okay, follows the rules. Now I'm sliding this under through the triangle over to here, slipping this guy here underneath, push, like that. And now you see that it still remains three colored. By choosing an appropriate color here, it all works. And I can keep on going. You can check the different cases of this. That's where this is a nice exercise. You can try it out yourself with three colors and the three color rule, 3 or 1. And you'll see that no matter what you do as you push it around, it will retain its three coloredness. So being three colorable is a property of the knot that remains no matter how you push it around. On the other hand, if you had an unknot would be something like this, a little circle, and you wanted to color it, well, there's only one color available for the unknot. And when you push it around, it will still be able to be colored with one color, but you won't be able to color a version of the unknot with three colors. You'll only be able to color it with one color. You can try. And so that is the proof that the trefoil is knotted, because every diagram obtained from the standard trefoil by topological changes uniquely inherits a three coloring, but an unknot diagram can have only one color. So that's a simple combinatorial proof that the trefoil knot is knotted. And it is, in fact, the simplest proof that I know. It requires some more subtlety to handle knots than to handle links. So let's see where we are now. I just want to re-summarize what I did about coloring, and then we'll leave it. I'm not going to use coloring in the rest of the talk. I just wanted to show you this to give you a bit of knot theory that you could play around with for yourself if you wanted to. So I have a color A and a color B, and then I have the new color on the other line. And if A and B and C are the three colors, then I have to take the third color here. So that means that red times blue must be equal to green, and so on. Two colors combine to give you the third color, the three colors. On the other hand, if this color was the same as this color, then this would be the same coming out. And that means that I have products like this. That the product of two colors, I'm sorry, we'll leave it here. I'm going to skip a couple of slides, but with the three colors, the product of any color with itself is equal to itself. A times A is A. A times B is C. And then I am remarking that this algebra of three colors can be thought of as a system of discriminations. A and B are seen to be different because when they combine, they give a new thing, C. and it closes cyclically on 3 in this case, a very simple algebra. But it's not associative, just for fun. Notice that. If you take A times B, you get AB, which is C. If you take A times AB, you get AC, which is B. It's not associative, and that non-associative structure is mirroring non-associative things that are happening with the knots. So now let's turn to knotted vortices and reconnection. This is a picture of a knotted vortex in water produced by Kleckner and Irvine around 2012. And this was the first time that anyone actually produced a knotted vortex in water. The idea of knotted vortices in a fluid goes way back to Kelvin and his theory of vortex atoms. I think at this point I'm going to do this in slideshow form. Kelvin's theory of vortex atoms was a long ago precursor of string theory, the idea that particles or atoms would be extended objects, and he thought that they were knotted vortices in the luminiferous ether. And he theorized about that. Eventually, his theory came a cropper because people gave up the ether, but it also had its own difficulties during its time in the 1900s because there's the question of the stability of the vortex and many other questions of this kind. But it was a lead, and people were thinking about it a lot in the 18th century. And I said, yeah, in the 1800s. And it was popular. For example, the mystics Ledbetter and Besant had their vortex atoms, which they felt were the way in which the spiritual world came into the material world. And if you were to read the wiki on the history of knot theory, you would find a nice listing of the people who were involved from the very beginnings of the knot theory. And you might find, I haven't looked at the most recent wiki, a statement like, knot series ceased to be of great scientific interest after the luminiferous ether was banished. But of course, this is not true. The idea of knotted and topological physics continues to this day, but not in the form that Kelvin had it, of course. So, as I said, it wasn't until around 2012 that Kleckner and Irvine actually produced definite knotted vortices in a fluid that you could see. It's curious, they aren't so easy to see in nature, and you need to create vortices, and then you need to somehow make them knotted. How are you going to do that? Well, this is the idea. This is how to make a smoke ring or a vortex ring. This is their method for making a vortex ring. The cross-section of this template on the right, this teardrop like that, and if it moves down through the fluid, there will be vortexing at the tip. And this is rotated so that you have a circle. And so if you move this red template quickly down through the fluid, give it an impulse, a vortex ring of fluid will come out of the top, and it could be a water vortex ring, like that. So that's how to blow a smoke ring in water. You can do the same thing by having smoke in your mouth and giving an impulse so that instead of moving your mouth backward, the air moves forward, the smoke moves forward across your lips, and then the smoke ring comes out as a vortex. So you can make vortices, unknotted vortices, by doing this technique, but their technique of moving a template, they had the good idea of making a knotted template. So they make a knotted template, and they made a knotted template by using 3D printing, and then they could tinker with it until they got it right, and then they can produce knotted vortices. So here's an unknotted vortex being produced by their method. And they use high-speed photography so that you can get a look at these guys. And they tend to disintegrate very rapidly. Here's the knotted vortex. So you see it's palpably a trefoil knot, and there really is a knotted vortex there. Yeah, I don't have a movie of it continuing to evolve, but when it does continue to evolve, it disintegrates, and we have to talk about, and that's what we're interested in here, is how does it disintegrate? Let's watch it one more time, though. Oops. There. I hope you saw the knotted template at the bottom. Now here's one of the ways in which the disintegration happens. These are stills, of course, and you'll see some motion pictures. Two bits of line vortex come near one another, and they undergo reconnection, just like we were talking about abstractly in the knot theory. They undergo reconnection. They go through a chaotic regime and end up reconnected the other way around. Like that. And what tends to happen with these knotted vortices in the water is that they just disintegrate into unknotted things by a series of reconnections. What happened there? Sorry, something. Okay. We studied this, and they use a model which is a mathematical model of vortexing, which is very interesting, so that you can study the reconnection by looking at the evolution of an equation. And in particular, what you do in this kind of modeling is you use a nonlinear Schrodinger equation, and the vortices, the line vortex, is a line of phase defects in the wave function for this nonlinear Schrodinger evolution, the Gross-Pietkiewski equation. So it's like this. The phase along the knotted curve is utterly ill-defined. It's a phase singularity. And then you watch how this behaves under the evolution, and you see reconnection. So you can do computer studies like this. So let's go back to a knot theorist or a topologist point of view. Under what conditions do you get this reconnection to happen? You need that the vortexing, the flow of the fluid should be the same in the intermediate position between the two line vortices. That if the flow is opposite, remember the flow is circular around the vortex line. And as you see here, it's going counterclockwise around one line and clockwise around the other, and that means that in the in-between of the two lines, it's flowing in the same direction. And so I will, for my diagrammatic purposes, orient the line in such a way that the right-hand rule tells you the circulation direction around the line, all right? And that means that will have the possibility of reconnection. Then they can get into a combined flow and it can change to the other one. I do not understand, and probably other people do well understand, exactly under what local conditions should it be that it will transform by reconnection from one to the other. But it does, and you see it happen. So we're just going to consider what are the topological possibilities here. Let's suppose we have reconnection. When can we have reconnection in a diagram? Well, if you have crossing like this in the middle here, so I can point, you see that this is oriented oppositely to this one, so reconnection could happen right there. And when it does, you'll notice that when I reconnect, the orientations are still compatible, which is convenient for diagramming it. So that this is the before shot and this is the after shot of a recombination right there. And if we started with a trefoil knot and we did a recombination right there, we would end up with a simple link. And if we did one more reconnection right here, we would end up with an unknot. So apparently it takes two reconnections to completely undo the trefoil knot. This leads to a natural topological question. What is the least number of reconnections that you need in order to undo a knot or a link? And that's what I'm going to be thinking about here. Let me go back. Yeah. So here's a more complex example using that evolution. Here's the 6-2 knot. And here it is evolving and changing to a link and then changing to a trefoil knot and then changing to a simple link, a Hopf link, and then changing to an unknot. So that's an example of this kind of situation. You can see what happened if you look at a diagram here. You can see where the reconnections occurred. I like to be able to point. There a reconnection occurred here and that resulted in a link. And then another reconnection occurred and we ended up with a trefoil knot, a reconnection here. And then the trefoil knot can turn into a Hopf link and the Hopf link can turn into an unknot. And apparently we needed quite a number of reconnections. We needed, how many reconnections did we have there? Let's do it again. Well, no matter. We started with this and we turned it into a link, 1. Then we turned that link into a trefoil knot, that's 2. Then we turned the trefoil knot into a Hopf link, that's 3. And then we turned the Hopf link into nothing, and that's 4. So it looked like it needed 4. Does it really need 4? That's the kind of question I'm concerned with. In the physical situation, you might find an evolution, a pathway, and takes a certain number of reconnections along that pathway. Is that the least number? How is it related to the least number? So I want to think of this in a space-time framework for the sake of the topology. So I'm going to think of a reconnection as tracing a surface in 4 dimensions. That's the world line of the vortex. It starts out one way, and after a little while it turns into the other one, and the surface that it traces out under reconnection is a little saddle, a little bit of saddle. And then for our topological point of view, we allow births and deaths as well for these surfaces, and we think of all sorts of different evolutions of this kind. And this is a topological context that has been studied. We ask, what is the least genus surface that the knot will bound in 4 space? But you see that every time you produce a genus, I guess I want to point again, if you produce a genus, you started here and you went through a saddle and then you went through another one and ended up back over here, you see that for every bit of genus that you produce, every hole in a toral or higher punctured surface situation, you're going to have 2 reconnections. So every instance of genus is 2 reconnections. So we can draw a diagram, a surface diagram corresponding to what happened to the trefoil knot. Here's the trefoil knot, and it went through one saddle and ended up as 2 components, and then it went through another saddle and ended up back as 1 component, and the entire surface, the world line, which I call the cobordism associated with it, that is genus 1. So for having genus 1, it ended up having 2 reconnections. So you see the idea. Look at the world line. Now, this is a picture of what we were looking at in the experiment. here's the 6-2, and it went through a reconnection here, giving us a link, and then it went through another reconnection over here, giving us the truffle knot, and then we needed 2 more to get down. But here's the topological fact. You can switch a crossing by using 2 reconnections. You can get a cobordism between a knot and another knot through one genus by doing 2 reconnections that switches the crossing. And I want to convince you of it here. Let's take a look. I put a little twist into the knot line topologically so that I have a vortex line going this way and another one going in the opposite direction, and then I undergo a reconnection. Now you see that this just goes underneath and underneath, so topologically you can pull it out and push it back over the top and then go through another saddle, and lo and behold, you switch the crossing. Okay? So you can do that topologically. You could wonder whether it will happen physically, but you can do it topologically. And that means that you could, if you wanted to, get the truffle reconnection by doing crossing switch. For example, you could put in a little extra curling in the trefoil, then go through a reconnection, then pull that back and push it underneath and go through a reconnection, and lo and behold, it's unknot. A little bit curly, but I'm not. Exactly as curly as it was to begin with, as a matter of fact, if you think about it. But you see, that's an example of what I said, but it's no more efficient than it was before, right? 2 reconnections undo the trefoil. But now let's go back to our 6-2. 6-2 happens to be unknotted if you switch one crossing. It's right there in the middle. Switch that crossing. And now look carefully at it, and you see you can slide this arc over and pull it around, and it just unknots. So you can unknot it in one crossing, which means that you can undo it by reconnection with exactly 2 reconnections rather than 4. So the minimal, after some work, will turn out to be 2, not 4. So that's my topological problem. What's the least number of reconnections needed? And if you want to imagine a scenario in which that would actually happen for the 6-2, here we can have a little curl here, reconnect, pull it back, put it back over, reconnect, and it's unknotted. So we've seen that a physical sequence of reconnections takes the 6-2 to the unknot in 4 steps, but in principle it can be done in 2. And we expect this sort of difference between physical pathways and available topological pathways. I'm hoping to get back with William Irvine and do some more computer experiments about this particular point. Now, what about lower bounds? Well, then you can go over to the world of topological invariants and kind of things that I was talking about at the beginning. And there's a well-known invariant of knots and links called the signature. And the signature happens to be a lower bound on the genus. That the genus in the foreball of that world line is less than or equal to the signature is less than or equal to twice the genus in the foreball. But the genus in the foreball contributes to the reconnection number, as we know. Twice the genus is less than or equal to the reconnection number. That's what we saw before. Every time you go through a genus, you're doing reconnection. So that tells you that the signature is less than or equal to the reconnection number. And from that, we can prove that the reconnection number of the truffle knot is 2, the reconnection number of 6-2 is 2. But there's more. Never mind the definition of genus. Now let's see, how much time do I have left?
You want questions as well, including questions, you've got 21 minutes.
Okay, so I have about 20 minutes or thereabouts before questions, right?
No, including questions.
Oh, including, yeah. Okay, right. So I'll try to adhere to that. Now, I want to show you some something about the geometry of the knots, the surface geometry of the knots that's important here. Here's the trephine knot. And suppose that you replace every crossing by a smoothing like this, oriented, like that. All right? Then you get a collection of circles in the plane. And there's a very nice construction due to Seifert back in the 1930s that produces a surface, like a soap bubble surface, whose boundary is the knot. What you do is you span each of these circles with a disc. And here I've spanned the outer circle with a disc which is going out in the plane so you can see it easily. But it might be like a bubble surface and coming up like this out of the plane. And then you put a little twist of surface in between each of the circles, just like in the knot, and fit it together, and you get a soap bubble kind of surface whose boundary is the knot. Okay? That's called Seifert's surface. And we're interested, for topological reasons, in the genus of such surfaces and so on. Now you can also produce the same kind of surface by reconnection. If you were to do one of those oppositely oriented reconnections at every crossing, you see, you get two circles just as before with some curliness, but it's really the same construction. And so you see that, at the very least, we can destroy the knottedness of any knot by doing one reconnection at every crossing. So that means that the crossing number is an upper bound for the reconnection number. You can at least do that. You'll probably do better than that, but that you can do. Question? No. Okay. Now, we'd like to know the genus of the surface that I just produced. And I'm telling you that twice the genus of that surface is equal to the number of crossings minus the number of these Seifert circles plus 1. And this number, crossings minus Seifert circles plus 1, is going to come up in trying to think about reconnecting anyway. So I'm just asking you to memorize this and notice what happened here. I'm not going to derive it, but you can find the genus by using Euler's formula for the genus in terms of vertices and edges and faces. The point is, what is the calculation here? How many crossings? 3. How many circles? Seifert circles? 2. 3 minus 2 is 1, and 1 is 2, and divide by 2 and you get 1. But if we're thinking about reconnection number, then the estimate on reconnection number that's going to happen here is 3 minus 2 plus 1, which is 2, right? 3 minus 2 is 1, and 1 is 2. And that's the reconnection number for the trephine knot. And this is not an accident. You'll see what happens in a moment. Here's the theorem, that if you have a positive link, and that means that all of the crossings are positive. Oh, I forgot to tell you, let's go back to a picture that has an oriented crossing. This is an example of a positive crossing. Crossings have signs. If you put your fingers of your right hand in the direction of the overcrossing line, your thumb would point in the direction of the undercrossing line. That's called positive. Knots can have positive and negative crossings. A nice class of knots are the positive knots where all the crossings are positive. And the result, the result is that the reconnection number of a knot is always greater than or equal to that number, C of k minus S of k plus 1. It's always greater than that if the knot is positive. And I'm also going to show you that that's sufficient. That number right there is sufficient number to undo the knot by reconnection. So it's actually equal to it. So that's the result. That if you have a positive knot or link, then you can prove that the reconnection number is actually equal to this. In order to do this, one needs to use some topology that comes from that idea of Kovanov. It's called Rasmussen's invariant. So I don't know a simpler way to do that. Now, I think that it's probably better for me to skip any further discussion of the Kovanov homology other than to tell you that it comes from that and show you the geometry of how this works. So I'm telling you that by using some topology, which takes some study, one can prove that the reconnection number really is equal to the number of crossings minus the number of Seifert circles plus 1. That you can do it with this many reconnections is interesting to see. And so we'll finish by seeing how that works. Here's an example. Here is a nice positive knot. We're looking at it right here. And here is the Seifert smoothing of it, right? I've eliminated every single crossing. I'm not putting the little curls because as I said, if I do reconnections at every one of these, I'll get a lot of these curls like you see below, but the circles that I get are this configuration of circles. But I don't want to go all the way down to that. What I'm going to do is I'm going to notice that I can chain the circles together like this. This one to this one, this one to this one, this one to this one, and that one to that one, in a chain of little circles like that. And if I left them connected to one another, I would have an unknot. And so I don't have to go all the way down to the unlinked. I can go down to an unknot, which is the result of chain connecting all the Seifert circles. How many of these crossings would I leave alone in order to get the chain connection? Well, one less than the number of Seifert circles, right? Here I have 1, 2, 3, 4, 5 Seifert circles, and I have 1, 2, 3, 4 chain connections, one less. 5 Seifert circles, 4 chain connections. So I only need to do the number of crossings minus the number of Seifert circles plus 1 in order to get down. I leave all of these alone. I'm leaving these alone, or those 4 alone, and I reconnect on all the other crossings, and I end up with this unknot. Now, that you can see it's an unknot is because it's chain connected in that way. So I get down to an unknot by using C of k minus S of k plus 1, which is 6. And so by my theorem, I know that this knot has reconnection number 6. And this is a topological property. You could take this knot and you could make a much more complicated version of it or some other version of it, pushing it around, and then look at what kind of reconnections could occur. Reconnections could occur in any old way, not just this way. And the theorem tells me that the number of reconnections needed to get it unknotted is going to be 6 or more. So that's the theorem. And the interesting thing is that theorem really does use some non-trivial topology on the one hand, and it speaks to what can happen physically on the other. Of course, if you go the wrong route, you can end up higher. For example, if you want to undo this link, a wrong route would be to reconnect right here in the middle. You'll go down to 2 simple links, and they require each 1 more. And you would end up with a reconnection number of 3, but this actually has a reconnection number of 2 by doing it here and here. Just a nice example. I'm going to reconnect here, and I'm going to reconnect here, and I have an unknot, you see? So this can be reconnected with 2, but one of the natural sequences is 3. Okay? So that's the way this works, and you can, there are other knots that are interesting to consider. This is a torus knot. Let's use the slideshow. Here's a torus knot, and in the case of a torus knot, when you do the Seifert circles, you get 3 of them in this case, in general, you can count how many Seifert circles you get, and if you have a torus knot, that winds p times around the torus in one direction and q times around the torus in the other direction, then you find that the reconnection number is going to be p minus 1 times q minus 1. By this method. So, since we know the reconnection numbers for positive knots, there should eventually be many experimental results relating to this fact. Experimental in the sense of evolutions of a system like the Gross-Piatowski equation to see whether the minimal number of reconnections is actually achieved under certain circumstances. So that's the mathematics in relation to the physics in this talk. But now I want to show you an experiment by Professor Alexienko. Oh, we're almost out of time, but this is a fun experiment, so let's look at it. You're going to see this happen in the experiment. He has a vortex, a line vortex, and it's in a turbine-like situation where the water is being rotated around and around, and the turbine is wider at the bottom than it is at the top, which allows the vortex lines to float upward and then interact with one another. Because you see, if the vortex line, which has a direction upward, and the other one has a direction downward, then they can interact. Well, and then it interacts and ends up producing a link, so the topology got more complicated as a result. Here's the film. Up and reconnect. Hard to see, but here's some still shots. Going up, underneath, coming nearby itself. And now you have to watch the directions. Going down, if we give it a direction, and then coming back around and going up, you see? So these are vortices that can reconnect. And they start being pulled in near one another into a region, and then I don't have intermediate photos here, reconnect. And there's the link as a result. So it's possible for the topology to become more complicated under certain circumstances, and the phenomena of what actually goes on is quite remarkable. Let me show you one or two more Alexienko films. Look at this one. You see those filaments? The vortex gets near itself and interacts with itself, and you'll see filaments going back and forth across like that. Here's another one. Oh, yeah, produced a ring and it shot off. There, that's a good one. We could slow that down a little bit. Just to show you, there we go. So here it's getting nearer to itself. And now it's undergoing the process. And now you can see how quite complex and filaments in between as it transform. Look at those filaments going back and forth between the loop and the main vortex as it transforms into the other form. So lots of questions about modeling here, and there is some work about modeling these, of course, but I don't think it's fully understood. In order to model it very realistically, you need a combination of molecular substrate and the average properties of the vortices as well. Lovely filament production in that one. So that's my story about the vortices and their topology, and I'll stop now. Oh, by the way, of course, if you wanted to reconstruct or come back to a theory like Kelvin's, then maybe you should think about, well, maybe all of these issues, these multiple level issues and the difference between chaos and topology and all of this may well come in to a theory that makes vortices part of fundamental physics. This is this is fundamental, but it's not fundamental particle physics, and one wonders what it would be like to really understand vortex topology at the level of particle physics.
Okay, thank you, Lou. And have we got any questions from the audience here or from the
Virtual.
John? Yeah, the virtual audience. Yeah, the audience.
A quick question, Lou. Certainly, fascinating speculation as to the application of particle physics. Obviously, going right back to Kelvin. Any possible applications of spin phones?
Well, spin phones is a theoretical construct that is thought to underlie the possible limits of them, which might be smooth manifolds. So spin phones is to the smooth manifolds of general relativity as maybe the molecular substrate is to the apparently smooth properties of these vortices.
That's almost exactly the analogy I was thinking of.
So I think if one wanted to look at vortexing in spin phones, that might well be very fruitful.
Thanks very much for that.
John,
fascinating talk.
you had a question? John?
Yeah, fantastic talk, Lou. Thank you, as usual. If we think about physical properties of these vortices that you have, I'm trying to think of this again in terms of spin, and in terms of vorticity of these things. How does that vorticity evolve? Because you're forming all of these different links. Some of them are smaller. Vorticity must be conserved physically in the kind of pictures that you've been seeing, but is there a measure of vorticity that you can have for these things coming apart, and a measure of spin then of these things as these things come to pieces, and how the spin is distributed as you form those links?
Well, one of the topological measures, which is something like vorticity, is called writhe. If I have a diagram, if I had a diagram and I have these little curls in the diagram, and I count the curls with signs, that's the writhe of the diagram. And there's a well-known relation, so there is the definition of the writhe of the diagram. At the diagram level, it's just the sum of the signs of crossings. But the writhe is actually a three-dimensional thing that you can measure by doing an integral, like the self-linking integral, like the linking integral, but a self-linking integral for the vortex. And in the diagrammatic that I'm using, it's definitely the case that the writhe is invariant under reconnection, because when you reconnect, you don't change the crossings at all, right? So you saw that in my diagrams. I started with the trefoil knot and I went along and I got this very curly object out the end, but it had exactly the same amount of curliness as the original. And but it has been experimentally confirmed that the space writhe of these vortices apparently is invariant under reconnection.
That's very interesting indeed.
So that's a kind of vorticity.
It's a kind of integral vorticity. So it's what you can count. So it's numerical, but not an integral vorticity in terms of. But I guess the integral vorticity, certainly for the physical thing, the integral spin must be conserved, angular momentum must be conserved. But if you think about these different things, moving at a certain velocity, so a big one would have more angular momentum than a small one, because it's simply larger, so your R cross P is going to be bigger. And that has to be conserved as well, but that's a different thing to the writhe, which is counting the number of circulations in an integral way, isn't it? Okay. Anyway, it's great fun to think about these things and see how.
Yes, it is. Yeah.
Great fun. Yeah.
Any further questions or comments So,
Hi Lou, thank you so much for sharing this talk. I just had out of curiosity,
Can the speaker come forward so we can hear him?
yeah. So the reconnection number,
in front.
the reconnection number, like it of course the number of crossings being an upper bound makes a lot of sense, but then the twice the genus being a lower bound, but then getting this really clean formula is it all coming from Euler, or is it a combination of Euler and what was that, the Rasmussen invariant? Or
Well, no. Yeah, you see, there's a subtlety in the Rasmussen invariant. The invariant that I described to you at the beginning, the bracket polynomial, is unoriented, right? So that means that it's a sum over evaluations of all possible reconnections, irrespective of orientation. So it isn't going to directly talk to our quasi-physical problem where I'm only interested in oriented reconnection, right? But then remarkably, by going more deeply into the properties of those states of reconnection, all possible states of reconnection, one can ferret out something about the oriented ones. And so that turns out to be subtle. And it's the same subtlety as finding the least genus orientable surfaces that bound a knot.
Chris, how you had a question?
What was Ed Witten's interest in this? Is this related to string theory somehow?
Oh, well, yeah. Well, Ed Witten originally was interested in these knot polynomials back in the 1980s because Michael Atiyah gave him a puzzle. The puzzle was, can you interpret using quantum field theory the Jones polynomial? And Witten realized that this was in the same arena as understanding the properties of a curve in space through the holonomy around the field, watching a particle go around the curve and come back in a gauge field. And he understood that by functionally integrating such things, he could get at these invariants. So he wrote a beautiful paper called Quantum Field Theory and the Jones Polynomial in 1988. But it's related to gauge theory and statistical physics related to gauge theory. So it indeed is related to his interests. And it turns out that later these things are related to string theory as well by what's called the ADS-CFT correspondence. And people are still studying how are these knot polynomials and their generalizations, like cobordism homology, related to the string theory. So whether that end of things, well, I don't know how to describe what's going on recently to you in any coherent way in that direction. But that interest remains alive. There are a lot of physicists who are working on the covariant homology and things in relation to string theory. Some names may help if you want to look them up. Sergei Gukov, G-U-K-O-V, for example.
Thank you.
Okay, you got a question, Andrew?
Yes. As I saw the films, the filaments arose before they made a decision about which way they were going to reconfigure their junction.
Yeah, absolutely. And in fact, if you had what you saw in one of those films was two vortex lines that couldn't reconnect because they were spinning in the wrong direction. But they, nevertheless, when they came close, filaments went back and forth between them.
What physical property does the filament looking for in its indecision about which part of the form it belongs to?
Yeah, I don't understand what promotes the directionality. That's a good question. Maybe other physicists understand, but we see that in these situations there somehow is a directionality and it goes from this form to this form. Why? Why did it do that, right? I don't understand that directionality.
It looked like a
There's got to be an energy reason. It must have been, lower energy in the after than before. That's always the reason, but why?
If you have in Birkeland currents, for example, you have attraction or repulsion depending on the relative vorticity of adjacent filaments. So to have an exchange, as we've seen there, I'm looking forward to can we post, are these things posted somewhere so we can stare at them and look at them and...
I think I put the films and everything into a Dropbox folder that's available. I can send you the link to that Dropbox.
Please, yeah, of course, everyone, that'd be really cool, yeah. I'd like to stare at these things. That was a good, that was good observation on Andrew's part there. I hadn't spotted that one. I'd like to have a look at those things and see if anything comes to mind.
Sure, I'll look for one of my ANPA emails that has everybody's name on it, and I'll send the Dropbox link.
Okay, thank you.
Could ask a question about something else. I wonder how much of the literature after Kelvin's vortex atom was filled with stuff about it.
I missed the last part of your sentence. After Kelvin's vortex atoms, and then
How
what did you
much
say?
of the physics literature was filled with papers about it?
Yeah, if you think about the smoke-filled rooms and all of those smoke rings they were blowing, that's probably quite a...
Yeah, you're like a collection of Kelvin literature. Is that what you're saying?
I'm interested by the parallel with string theory. Endless string
Sure.
theory. Was there endless vortex atoms material after Kelvin's vortex atom?
Yeah, I have looked at some of Kelvin's writings, but I haven't tried to track all the literature on that. That's a nice scholarly project.
It will be very interesting to know.
But you know that there are people who wrote afterwards in a similar vein. There's a physicist named Herbert Yala who in the 1970s got it into his head that elementary particles were quantized knotted flux. And he wrote a number of papers about that, qualitative, and very beautifully drawn, beautifully illustrated. He was a good physicist. He did a lot of other work. But that work wasn't picked up by other people. And then more recently, people have wondered whether knotted gluon field might occur. Because in proton-proton collisions, you have you get what are called glue balls, loops of gluon field, because a quark, anti-quark pair gets blown out by the proton-proton collision, and then the ends reconnect, come back together, and you get a loop of gluon field, at least theoretically. And why couldn't those loops be knotted? So people have speculated about that.
Okay, well that's fantastic talk, and thank Lou again. And all the speakers today, and that ends our meeting. That ends ANPA 43. So on to ANPA 44 next year. Hope everybody can come in person next year.
Where will it be?
Are we going to be in Liverpool next year?
That's the plan A at the moment.
Can I just tell Lou something? Hi, Lou. I'm sorry I sent you so many.
Hi, Sydney.
Hi. Sorry I sent you so many emails. Just ignore all of them except the last one. Sorry about that. I was just correcting things.
Okay, we'll be talking.
Thank you.
Okay. Okay, so good to see everybody. And it'd be good to see everybody again in a year's
By the
time.
way, huge vote of thanks to Peter and his fellow organisers.
Andrew did the local organisation for this place.
And Andrew,
And Barbara.
And Barbara.
Barbara. And I
give them a round.
Well,
so that's it then. Oh.
in a naughty sort of way. How very weird.
After that.
If it hasn't gotten you then. Yeah.
Philip, how are you?
I've had COVID since the
Oh, jeez.
laugh thing. But,
Spencer Brown was a
only
super
men,
spreader
I think.
event.
Yeah. You're one of at least 4 cases.
Like 6 or 7 people.
Was it 6 or 7?
Yeah.
Yeah, Graham
A lot of
went
people.
down.
Graham.
Lowry went down. Randy went down. I don't know who
May
else.
see you next week.
Florian.
Yeah, see you next week on Monday.
Yeah, send me an email. The rest of you, I'm going to turn the machine
Good to
off.
see you, Lou, by the way.
Good to see you, Mike.
Yes, it's been much too long.
And Philip, I suspect we had wanted to have a conversation about some things. We could, if we had exchanged some email, we could probably find a time.
Okay, great. Thanks, Lou. That would be really terrific. Thanks so much for your talk today. I'll send you when I'm a bit better, which should be next week, I hope.
Yeah.
It'll be really good.